All right, so this is what an accumulation function is. It's a function that's in terms of an integral, and you're accumulating area under the graph. And the only thing you really need to be careful of is where the accumulation starts, because people will sometimes just start at 0 no matter what. It starts wherever it tells you it starts. So for this one, our accumulation is going to start at 3. So that's what an accumulation function looks like. And what we're going to do here, and I really like teaching this lesson because it ties together so many things we've learned before, and everyone kind of like makes connections between everything, and it's great. Remember when we did all of this stuff? First derivative test, second derivative test. We're going to revisit all of this from the point of view of the accumulation function. And guess what, guys? None of the answers changed. They're all still the exact same reasons as before. So it's cool. It's comforting. It's like, oh, okay, those are still the answers. Yeah, and yeah, sweet. People end up liking it because it's actually not new information. And then people make connections between stuff. It's all really good. So this is all, first derivative test, second derivative test. So the first thing we're going to need to do is get a derivative, and that's why I just taught you how to do a derivative of an integral. That's why we just did that, minutes ago. So all you're going to do here is take x and plug it in, and that's going to give you f of x. And so it would be really helpful if you had, some information about f of x. And the way that they give you this information is through a graph. So I'm going to draw the graph of f of x for you. And yes, you're going to have to draw it too. And I'm really sorry. I know when I teach this in person, I'm like, yeah, you have to draw the graph. So this is going to be the graph of f of x. So let me draw it, and I'll label all of the points for you. Except for that one. That one's the origin. I think you guys can see that one. All right, so yeah, guys, I know it's a little bit tedious. You have to draw that graph, but it's only a collection of a few points. Here, I'll zoom right in on it. So it looks like some mountains there or something, but you need that in order to answer any of the questions. So you're going to have that. So I'm going to wait like one more minute, and then I'll start going through the problems. What I'm going to do is like parts A, B, C, D, E, F, G for this, and we're just going to go through the entire process exactly like we did back in Unit 5. And we're just going to revisit all of that information. So again, I really like teaching this because it's actually not new, and it's like an aha moment for a lot of people, like tying things together. All right, so let me zoom back out and we'll start going through this. So again, I'm just going to letter everything like A, B, C, D. So for letter A, we're going to find the critical points, and I'm going to put justifications for everything so we can review how to do this. So g of x, which is the function that we're talking about, this accumulation function is the one we're going to write all our statements about. So all the sentences should start g of x is or g of x has. This is the guy that we're discussing, right? So g of x has critical points at x equals. Now, a critical point, I'm going to ask you guys, critical point is where a derivative equals 0. And our derivative is this graph right here. So hey guys, where does this graph equal 0? I'll give you a hint. There's 2 answers. You can just give me one or the other. I think between you, we'll get all of them if I get a few people to answer here. Where does this derivative equal 0? Good, 0 is one of them. Nice. And good, 6. Good. X equals 0 and 6 because derivative equals 0 there. So those are our critical points, and that's the justification. All right, so next we're going to do increasing and decreasing. On my sticky note, this is a little confusing because I wrote it with F. Just pretend this says G, G prime, and G double prime, okay? Our function is increasing where the derivative is positive, decreasing where the derivative is negative. All right, so let's do increasing first. G of X is increasing wherever this derivative is positive. That means above sea level. So hey guys, where is this graph above sea level? From where to where? Yeah, good, 0 to 6. And oh my gosh, aren't those the critical points we just talked about? Oh, crazy, all right? So G of X is increasing 0 to 6 because G prime is positive there. And then the sibling statement, G of X is decreasing wherever the derivative is negative. That would be below sea level. So that's going to be -2 to 0, union 6 to 7, because derivative is negative there. And those are the exact same sentences we wrote back in Unit 5. They're not different. Like I didn't change it. This is actually like a review lesson, basically. The only new thing is that this is in terms of accumulation. All right, and then we're going to do relative maximums and minimums, which come from the critical points. So we're still looking at 0 and 6. This is all connected here. Let's look at 0 first. I'm going to ask you guys again, so heads up. At 0, we have a change from negative to positive. This goes from below to above. So hey guys, if there's a change negative to positive, does that mean relative maximum or relative minimum? Minimum, good, nice job guys. Negative to positive means minimum. So G of X has a relative minimum at X equals 0 because G prime changes from negative to positive. I'm going to make this fit there. G prime changes from negative to positive there. And then we're going to write a sentence about our other critical point, which is 6. And at 6, we have a change from above to below. So that's from positive to negative. Positive to negative means maximum. So G of X has a relative maximum at X equals 6 because derivative changes from positive to negative there. I know it's a bit of writing, but you'll be okay. And those are the answers. I can't really change them. All right, so those were relative maximums and minimums. Next, we're going to do absolute maximums and minimums. This is your candidates test. And for candidates test, you're going to check the end points and the critical points. So those are your candidates that you're going to put on this table. So our end points are -2 and 7. And then our critical points that we found are 0 and 6. So we're going to check our end points and our critical points. Now here's where the accumulation function comes in. And this is like the one kind of new thing. we're going to plug them into g of x, which is this accumulation function. And the accumulation starts at 3. So what we're going to need to do is find all of these areas under the graph, because we have to accumulate area starting at 3. So this is where we kind of put on the brakes, and we have to stop what we're doing and go and find all these areas. But we need to do that. So let's go and find them. So this first shape here is a triangle. So that is 1/2 base times height, which would be 1/2 times 2 times 1. So it's going to be 1, but it's negative because it's below sea level. So -1 for that little triangle there. All right, and then this triangle, again, 1/2 base times height. The base is 3, the height is 4. So that's going to give us 6 for that. And then I'm going to have a couple of trapezoids in here, and they're on their sides. So again, this is the height of the trapezoid. You want to like turn your paper and look at it this way. That's the trapezoid right side up. It's turned on its side. So trapezoid is 1/2 times the height. So the height is just 1. And then you add the bases together, which would be 4 plus 2. So that is going to be 3 for that one. And then the next trapezoid, again, 1/2 times the height, which is 1, and then add the bases together, which would be 2 plus 3. So that would be 5/2 or 2.5. I'm going to write that as 2.5 for that one. Again, I told you it was a little tedious, but you have to be able to find the areas of shapes. This is like your geometry review here. All right, and then another triangle, 1/2 base times height. So that's 3/2 or 1.5. So I'm going to write it as 1.5. And then this last little triangle is 1/2 times 1 times 1. So that'd be 1/2, but it's below sea level, so it is -1/2. So -1/2 for that one. And I get a lot of people that will want to like just find all of these areas up front before they even start the problem. You can do that too. You don't need it until you get to this chart, until you get to plugging them in here. All right, so we're going to plug in our endpoints and our critical points. These are our candidates to this accumulation function. So we're just going to start at 3. This is like our starting place. And so if we plug in -2, we want to accumulate area from 3 to -2. So that's from here to here. Now you're going backwards. So it's going to be a -6 and a +1. Everything is opposite sign since you're going backwards. So -6 plus 1, that will be -5 for that. And then 0. So if we go from 3 to 0, again, still going backwards, that's going to be -6. And then going from 3 to 6. Okay, finally we're going forwards. From 3 to 6 is going to be all of these areas added together. So 3 and 2.5 and 1.5. So that's going to be 7. And then from 3 to 7, well, it's that value of 7 that we just found. All of this area added together was 7, and then minus 0.5. So that would be 6.5. And this chart acts as your justification. So you don't need to write a sentence like we did over here, because blah, blah, blah. You don't have to do that. You just have to state the answer. So our absolute maximum is 7 at x equals 6. That's just the biggest result that we got. And the absolute minimum is -6 at x equals 0. That was the absolute lowest value that we got. And again, the chart is your justification. So that's everything from first derivative test. We did critical points, increasing and decreasing, relative extrema, absolute extrema. Now we're going to move into second derivative test, which are inflection points. So we're going to say g of x has inflection points at x equals, and I'm going to pull out my sticky note and we'll review what an inflection point is here. An inflection point means a change in concavity, concave up to concave down or vice versa. So that's where the derivative graph, which is this graph that we're looking at, that's where the derivative changes from increasing to decreasing or decreasing to increasing. So one or the other, right? But this graph is gonna have a lot of inflection points because it turns around a whole lot. So reading left to right, we have an inflection point at 3. We change from increasing to decreasing. We have another one at 4. We change from decreasing to increasing. And then we have another one at 5. Graph turns around again. So inflection points at 3, 4, and 5 because G prime changes from increasing to decreasing or decreasing to increasing there. And I know that's a long way of saying that, but that's how you have to write them. So changes from increasing to decreasing or decreasing to increasing. That's where you're going to have inflection points. And then concavity. So G of X is concave up. And again, I'm going to pull out my sticky note here. Concave up is where our derivative graph is increasing. So wherever this graph that we're looking at is increasing, that's where G is going to be concave up. So we are increasing from -2 to 3. And then also this section here from 4 to 5. So G of X is concave up, -2 to 3, union 4 to 5, because G prime is increasing there. And then decreasing. So G of X is, oh, I'm sorry, not decreasing, concave down. Concave down when the derivative graph is decreasing. So concave down is when the derivative graph is decreasing. So that is going to be from 3 to 4. And then also from 5 to 7. So because G prime is decreasing there. So this is everything we did in Unit 5, just a big old review. It's just in terms of an accumulation function. So you have to find all the areas under the graph. Last thing I'm going to do is we're going to take this information and put it all together and actually draw a graph of G of X. And actually, let me scoot this down a little bit because I'm going to add on to the chart there. So I'm going to take all this information and put it together and just actually draw a graph. So this is where everything that we've written out kind of all comes together in one place. And so what I would start out doing, like the points that I would start out putting on here are the ones that we already found on the chart. Like we already found these points, -2, -5. So I'm going to plot that. So we've got -2, -5. We've got 0, -6. And then we've got 6, 7. And then we've got 7, 6.5. So just like kind of right below that. So I just plotted the points that we had already found, like they're already right there. So go ahead and plot those. Now those are the end points and the critical points. I'm going to add on to this chart. We also need to do the inflection points. So I have the end points and the critical points. I'm going to add on to there and do the inflection points. So we have inflection points at 3, 4, and 5. But these wouldn't be necessary to put on the chart. I'm going to kind of like block that off there. You don't need to put these on for your candidates test. This was sufficient for the candidates test, but I'm just going to add on to the chart so I can do my graph here. I need to plot these critical points for 3, 4, and 5. So let me slide this back down. Here's our graph. And again, our accumulation starts at 3. This is our accumulation function beginning at 3. So we're going to plug in these inflection points. So hey guys, if we plug in 3, if we do an integral, I'm throwing a question at you, so heads up. If we do an integral from 3 to 3, what is that going to give us? Like how much area did we get from 3 to 3? Yeah, good. Precisely nothing. Like you didn't go anywhere. So you didn't accumulate any area. So yeah, nothing. So we get 3, 0. Good. Thank you for still being awake. All right, so 3, 0. You didn't accumulate anything. All right, and then if you plug in 4, so now we want to accumulate from 3 to 4. So that's just this one little trapezoid in here, which was worth 3. So that gives us the point 4, 3. And then 5, we're going to accumulate from 3 to 5. So that's these two trapezoids in here. So that would be 5.5. Right, so last thing I need to do is just connect the points. All you need to do is connect them with the correct concavity, which I have right here. So you just need to connect the points with the correct concavity. So we want to be concave up from -2 to 3. So I want to be concave up for this section. So see how I'm making it like upwards, like a smiley face? So concave up for that section, and then concave down from 3 to 4. So you want to change it, make it bend the other direction. And then we want to be concave up again from 4 to 5. So concave up for that part, and then concave down from 5 to 7. So concave down for the rest of it. So that's cool. It looks neat. It's like a little, like, I don't know, a fishing hook or something. And so we actually drew a graph of this. We took all the information, put it all together. This is so cool to me. I don't know, because I know I'm a math geek, but this is like all the information about this graph, all the justifications, all in one place, and then we drew it.